we will deal with landing site characterization in the proximity of Marius Hills pit. This is a work that I did in cooperation with Angelo and Maurizio Paioli. We'll hear tomorrow, and other colleagues. And this is related to lunar caves exploration. So what are lunar caves? So caves do not exist just on Earth. We are widely used to see and visit beautiful caves in karst environment. So dealing with the dissolution and precipitation of limestone under the action of acidic waters that are going through pre-existing paths along faults, or exploiting some voids, some fractures, and creating beautiful shapes and beautiful caves. But this is not the only type of caves we have on Earth. We also have lava tubes and lava caves. So these are places that are formed during a volcanic eruption, typically a basaltic volcanic eruption, such as an Hawaiian type of volcano, a shield volcano, who is erupting very, very fluid lava, low viscosity, very high temperature, and very, very gentle slopes. If these conditions are met, a lava river can form, and eventually this lava river can carve the subsurface, the ground, entrench itself, and then eventually cool down at the surface, creating a ceiling, and then basically isolating the system, becoming very, very much thermal efficient. And so the heat is not propagated on the outside, it stays in the inside, keeps the lava very, very hot, and it continues to flow and to form these long lava tubes. There are very long lava tubes on Earth. Some in Hawaii reach up to tens of kilometers, up to, I think, 60 or 80 kilometers in Kazumura Cave on Big Island. And through time, there has been the hypothesis that these types of caves are also existing on other planets. They have been observed on the Moon and on Mars. And how you will detect them from orbit? Well, you don't see them on the ground, of course, but you see on the surface the collapse of the roof along their path. So you see alignments of holes that follow a sinuous path that basically represents the path of the lava underground. And eventually, if something happens, like tectonic movement, impact, the shaking, and the heat of the impact can break the roof of the lava cave, and you can leave collapsed pits. And so this is why we know and we hypothesize these things exist on other planets. Some of these are simply bowl-shaped collapse. You don't see the entrances of an underground void. Other types of collapses are informally called skylights, are basically collapsed pits that represent the entrance to an underground void. And we know that they exist because they have been observed on the Moon also. This is an old paper from Wagner and Robinson. There have been quite a few updates so far, and you see marked with a star-shaped possible collapse pits that seem to have an underground void space below the surface, whereas the round dots represent things like impact melt pits. If you remember, we saw Copernicus. I pointed your attention to a pit, a hole without a rim, but basically it was simply a hole with no continuation underground. These are other types of formation mechanisms, and I'm not super expert on that, so I will stick to those marked with the stars. And if you see, the vast majority of it are within Mar basalt units. So where you have this basaltic infilling made of lava, possibly very fluid, and you have something also on the far side. But most of them are found on the near side. By the way, it has been published a couple of years ago, a beautiful lunar cave catalog that you can explore in the RockNAC website. And there's a database that you can consult. There are lots of information about the morphology and the size of these pits. So how do they look like? This is how they look like. This is Marius Hills pit. I will show you where it is. It's here, close to the Marius Hills volcanic area on the Moon. And Tranquillitatis, no, this is Mare Ingenii pit, which is here. So This is the same collapse pit observed with different incidence angle of the lights and also different azimuth. Here the light in the first case is coming from right to left. In this other case is almost vertical. Here the observation conditions were so tilted that the satellite could observe it from a slanted angle, checking that there was actually a roof overhanging a void below. Here you see another example with the same boulder. You can see here and here, so it's the same. And you can even see the stratigraphy of the roof that stays over the void. It probably is full of it's made up of a pile of basaltic layers that made up the Mario basalt unit. Here you see the Ingeni pit. So this is very steep, very overhanging. And this is again sloping in. You have a sort of a funnel around this pit that is sloping down. But if you look from a slanted angle, actually this is not, yes, from a slanted angle, you can see still a pile of probably basaltic lava flows that one is stacked upon the other. So this is how they look like in the case of a skylight. So they can be observed until a certain degree of let's say orientation. Some of them you can see the bottom, like in this case. Others, for example, the Mare Tranquillitatis pit, which is this one, you cannot see the bottom. So we know from the shadow cast by the pit itself on its walls that that pit in particular is at least 60-70 meters deep, but we do not know how deep it is. We are not able to observe the bottom. So it means that they can be very, very, very deep. I will talk specifically about Marius Hills pit, and I will give you some more information. So this is the area. This is on the near side of the moon. This is its exact location. It was discovered more or less 14 years ago in 2009 by Junichi Aruyama from JAXA and using the terrain camera of Kaguya, which we use today and we talk about also last days. And it's located here. And the location is interesting because it's basically at the top of this rill. This is a rill, probably this is a vent from which the lava was flowing out. And here you have basically a punch hole. You see a hole. So that means this probably was either a lava river that is entrenched and cooled down, but since the roof is so thick, probably the formation mechanism was a bit different. We are talking probably about inflationary mechanisms, so lava that is injected below the surface and then creating its own way through the deeper level of the crust, creating very, very large voids. And if you observe it from above, you can infer its size. These were the calculation made by Gerber et al. About the size of this particular hole, and using the data also from the paper of Wagner and Robinson. So you see that from the shadow and from the size on the ground, you can estimate that the size is about 70 to 80 meters in diameter of the outer funnel. Then you have the inner part of the pit, which is, let's say, 10 meters, 10 to 20 meters shorter. So around 50 to 60 meters in diameter, more or less. And there's a regolith layer at the top, which should be around 4 to 10 meters. And then you see all these layers that we have seen from the slanted observation, and then potentially there's a void space. We do not know if the void space continues along the tube or simply is something like that. So basically it ends up just a bit farther than what we can see. But these objects are potentially very interesting for many, many reasons. The first reason is that if one can access these voids, it's shielded from the micrometeorites that are hitting constantly the surface of the moon. It's shielded by cosmic radiation. It's shielded by the delta of temperature, which on the moon is very, very, very strong, and so on and so forth. It can be also potential cold traps. So they can be volatiles nested around here. So it's very interesting for many, many reasons for exploration. So we wanted to characterize that specific site, and to do that, we would use the Al-Rock NAC stereo DEM, and we refined it with the shape-from shading, and then an ortho image draped onto the DTM. So this is what I mean. If you take two stereo images, you put them together, if the surface is not variegated enough or it's very flat, you end up with this result. You get the topography, you see here the altitude. The whole, of course, is not resolved because everything is dark, so the stereo algorithm is not really able to characterize the bottom of the hole. But the whole surroundings, they can be reconstructed. But you see that there are artifacts. They look like a fabric, more or less. These artifacts are generated because the images are very smooth. If you take the illumination condition information of one of the stereo pairs, and from the illumination condition, you can infer whether you have a depression or a convexity. You can couple those with the DTM and you can refine the first, let's say, the first result of the stereo matching, creating this. And if you compare it with the actual ortho image, you see that lots of features are resolved. And you can enhance basically your perception and the ability to detect, for example, small craters that you may want to avoid. We created a summary map of all the hazards around this area. And we calculated the impact craters by using the TPI. TPI basically used to calculate the things that are above or below the average of the surface. This is a good way to detect craters. So for those asking for some automatic methodologies, this is one of them. Of course, you have to tweak some parameters, but this is quite good result. We can calculate the depth. We do that by contouring all the craters and then calculating the delta between the actual topography of the contour and the bottom part. And so we can estimate the depth of such craters. So the deeper ones being more or less 5 meters deep, and the shallower ones being like half a meter. And then we can calculate the slope. This is the same threshold you've seen over and over the past days. But if we put all this information together, we can create a hazard map of go and no-go areas, which is the one on the right. And we can place a landing ellipse, tentative landing ellipse here. Of course, we do not have any parameters for landing orientation, size of landing ellipse. This is a bit a guess, but it's, I think, an educated guess. So everything that is marked in orange is the sum of the tilts of the slope. We can go with some margins of uncertainty. The red areas are the areas where we do not want to go, either because the craters are too deep or because they are too sloping inside. And once we have this hazard map, we can try and design a traverse to approach this pit, because we may want to observe it from above with some instruments. We can deploy some instruments inside. But what to do if we want to put instruments inside? Before we want to navigate safely there. And to characterize the trafficability of terrain, we can do two things. One thing is to analyze more or less the size frequency distribution of the rocks that were analyzed by the Apollo astronauts during their EVA activity on the surface of a similar geologic setting, although not the same geologic setting. We can also use rock abundance maps based on thermal inertia, for example. We can also count boulders all around using the NAC camera, and we did that, and we found that there's a fairly low amount of relevant boulders, let's say. And then after that, we can approach the pit almost safely. And then what to do if we want to deploy an instrument inside? We want to see the best place free of boulders that can basically ruin our scientific analysis. And we can do the same thing by selecting a proper image from the right illumination conditions, so taken from above and with the sun basically almost at the zenith. And we can create density maps of the boulders. And we can calculate also a size frequency distribution and cut it to a resolution threshold here. So we can then guess which is the size of the boulders that we do not see, but we can expect based on this curve. We can also analyze in the very, very close proximity the funnels, because we do not see the funnels from the images here. We know that there's a bit of funnel from the ground towards the actual edge of the pit. And if we go with an instrument on the funnel, probably it's too slopey. We get to there's a chance that we topple down, we roll down, and we lose the mission. So to do that, we can also calculate a local slope analysis and try to detect small areas with tolerance that is available for our instruments. So this is a very, very short talk. And just to show that you can do also very local scale analysis around these objects, there is a paper in preparation by Gloria Tognon, who was the person that created also a Tsiolkovsky crater map about the Mare Ingegni pit. And this is a really nice also exercise about landing site characterization, also in let's say unconventional contexts, to try and explore also very difficult locations such as this one. I don't want to steal your time anymore. There is a break now, and I'm happy to take questions via chat. If not, we will reconvene in half an hour. We will have David Hodgetts by VR Science, who is going to talk to you about how we can do mapping in virtuality in 3D with his own software that he developed, and we are currently using in the University of Padova for our students, and it's performing really nicely. So thank you for your attention, and talk soon.